Okay, so we're going to cover a few things in Chapter 1, Section 3. The first one that I want to talk about, I'm going to kind of split these up into pieces in case you need to review one but not any others. We're going to talk about exponential decay. Now, exponential decay usually happens specifically in terms of half-lives, but there are other kinds of decay as well. For example, used cars usually depreciate between 5 and 10% per year, and that's a kind of exponential decay where the loss kind of evens out over time. So I'm going to give you guys first a general formula for how exponential decay works. So the amount, which I'm going to call A, is equal to the principal, or the primary value, the value at the beginning, times in parentheses 1 minus the rate of decay, and you need to make sure that you're entering that as a decimal. So if it's 2%, it's 0.02. If it's 50%, it's 0.5. To the power of, and now this is where I'm going to kind of mix some metaphors here, but I'll explain exactly how it works. I'm going to say n divided by lambda, and lambda is this Greek character here. Now let's kind of make sure everybody knows what each of these is. A is the amount. P is the principal, or the primary amount, the starting amount. R is the rate of decay. And for exponential growth, it's very similar to this equation. It's just that usually exponential growth in the real world has a compounding aspect to it, and so this R changes just a little bit when we have to deal with compounding. N is the amount of time. And in this case, lambda is, I'm going to call it the decay period. Specifically, lambda in physics is or chemistry is the half-life of a material. It shows up in a bunch of other places too, though. So I'm going to call this the decay period. All right, so let's start with the half-life example. Usually when people talk about half-life, they talk about radioactive materials, which is true. That is one place where half-lives come up, but it's actually way more frequently used when we talk about medication. So I'm going to specifically talk about caffeine first, because caffeine is kind of fun to talk about. So in general, caffeine, and this varies person to person exactly what the half-life is, has a half-life in your body of about 5.5 hours. Now, depends on your metabolism. Some people can metabolize caffeine more quickly, and they might have it as low as 4.5 hours. Some people metabolize it more slowly, and they might have it as high as 6.5 hours. Let's say that you're drinking like a double shot espresso. I think that has about 200 milligrams of caffeine. Say you're having that first thing in the morning, so at AM. Now we can track how much is going to be in your body by using this exponential decay equation. So the first question I'm going to ask is how much of that espresso, assuming you don't ingest any more caffeine, is body at, make the math not super easy. Let's go with 4 p.m. All right, so to do this, you're just simply plugging information in. So the amount that would be in your body is equal to the primary amount, which was 200, starting amount, the principal. 1 minus 0.5 is 0.5, because if it's a half-life, R equals 50%, 0.5. The N in this case would be the amount of time. Now from 7:30 a.m. to 4 p.m. is 8.5 hours. And the half-life, the decay period, is 5.5 hours. Now from here you just have to plug it in, and I actually don't have my calculator nearby, so I will hopefully remember to cut this part. I'll be right back. All right, so at 4 p.m., left over from that espresso that you had in the morning, you still have roughly, I'm going to round this to the nearest whole milligram, 6 milligrams of caffeine. Now, this is essentially the way that your body digests, not necessarily food, but chemicals and compounds. They have a half-life, so things stay with you for significantly longer, A, than that you can feel them, and B, than that you would think. That's why drug tests work. For example, marijuana has a half-life of, I want to say it's like 10 days. Depends on your fat stores. If you're somebody who has a lot of fat on your body, it has a significantly longer half-life, but neither here nor there. Okay, so let's add another question to this, because that's an interesting question, is how much is going to be in your body, but that's like an Algebra 2 question, maybe even Algebra 1. Let's make this a little more complicated, and let's say how long will it take it 10 milligrams. Now this question is going to require a logarithm. I'm sure everybody remembers how to use logarithms. So we're going to set it up the same, only this time we know the amount. So the amount is 10, which is what we're looking for. Principal amount is 200. Half-life means this is 0.5. We don't know the amount of time, but we do know that half-life is 5.5 hours. Now, you need to break this down first so that you have a number on one side and an exponent on the other. Right now we have more than that. So first step is to divide both sides by 200. So 10 divided by 200, I should be able to do my head, 0.05. And then this is equal to 0.5 to the power of n divided by 5.5. Now, a logarithm, the way that works, if you have, say, 2 to the third equals 8, if you rewrite this in logarithmic form, the base of the exponent becomes the base of the log base 2. What is on the other side is what the log is being taken of, and then what it's equal to is the exponent, right? So using that idea here, we're going to have log base 0.5 going to be taken of 0.05. That's going to be equal to the exponent, and by 5.5. Now, evaluating this logarithm, again, I'm sure everybody remembers everything about logs. You can use your base change formula, because the TI-84 doesn't allow you to use logarithms that aren't base 10 or base E. ln is base E, regular log is base 10. You can change that by using the log base change formula. So the log base change formula, again, if you forgot from Algebra 2 or pre-calc, if you have something like, say, log base, I'm going to keep with this, base 2 of 8, this can be the same as log base 10 of 8 divided by log base 10 of 2, so long as it's the same base on both these logs. So it's log of the big number divided by log of the base. So using that over here, that means that we can do regular log base 10 of 0.05 divided by regular log base 10 of 0.5, and that's going to be equal to n divided by 5.5. Now, again, I'm going to take just a second to evaluate that. I'm sure some of you guys have done this faster. So we end up with 4.32, rounding to the nearest hundredth. This isn't equal to n. This is equal to n divided by 5.5. To find out what n is, we now have to multiply both sides by 5.5. Get 23.77, and this is going to be in hours. Now, so it takes roughly a day for that one double shot espresso to make it down to 10 milligrams of caffeine in your system. Now, this gets exacerbated if you're redosing on caffeine throughout the day. Luckily, a lethal dose of caffeine is super high. You'd have to be taking just an insane amount of caffeine every day for about a year before you'd get a lethal dose of it. But caffeine stays in your system way, way longer than you think it would. If you were redosing, this problem would become, it's a calculus problem, but it's later in the year. It's called a differential equation. All right, so this is reviewing how to do exponential decay in general, how to find an amount after a given amount of time, and then to find out how long it will take to get to a given amount, as well as a tiny bit of a review of how logarithms work. So this covers the poisoned problem that you guys will have on Google Classroom, and it covers a portion of what's on the book assignment for 1.3, and it covers the paper assignment from Monday. So there's 3 things that this kind of, well, 2.5, maybe 2 1/3. Next, we're going to talk about compounding interest rates. So tune in for that, and I hope everybody has a great day.